Okay, so in this video, we are going to be looking at two liquid tanks, and in those liquid tanks, we have water, and between those tanks, we have a manometer, and that manometer's job is to measure the difference in fill level between those two tanks. So we're going to first look at our definitions here. So A is defined as the difference in liquid level between tank number 1 and tank number 2, and B is defined as the deflection of the manometer. And it is worth noting that this diagram is also not to scale. So the objective here is to find the amplification factor, or in other words, the ratio of B over A. B over A basically tells us how many inches of deflection of the manometer do we get for every inch of liquid level difference between the tanks. So our assumptions are as follows. 1, we're going to neglect surface tension. 2, we're going to assume that we have an isothermal and incompressible system. 3, we're going to assume that we have a constant gravitational field. 4, we're going to assume that we have a constant uniform atmosphere. 5, we're going to assume that the specific gravity of the oil in the manometer is less than the specific gravity of water. And 6, we're going to assume that the tanks do not drain below the manometers. So our knowns here are the specific gravity of water is given as 1, and the specific gravity of the oil is given as 0.797. And again, the objective here is to use the manometer to measure the difference in fill level of the two tanks. And the amplification factor is just the ratio of how many inches of deflection we get in the manometer to the number of inches of difference of fill level between the tanks. So in this slide, essentially we've just drawn the manometer individually, and what we're trying to figure out is when the manometer is deflected more to the right than to the left, does that correspond to P1 is greater than P2 or P1 is less than P2? And we want to know this because we want to know how to draw our manometer depending on the situation we end up analyzing for this problem. So to determine this, what we end up wanting to do is apply the hydrostatic pressure equation between all of these key points, point 1, point A, point B, and point 2. So in this first equation, we apply the equation between point 1 and point A. In the second equation, we apply the equation between point B and point A. And in this third equation, we apply the equation between point 2 and point B. And what we end up doing is combining these equations algebraically until we get an expression for P1 minus P2. And that expression for P1 minus P2 ends up being the quantity rho W minus rho O times G times HAB. HAB is the distance from the hydrostatic pressure equation, so it's positive. G is the magnitude of gravitational acceleration, so it's positive. Rho W is given as greater than rho O in the assumptions of the problem, so this quantity is also positive. So in other words, this whole right-hand side is positive. So in conclusion, the manometer deflects just like this when P1 is greater than P2, or in other words, the manometer deflects more towards the side with the lower pressure. So to check this result, let's draw the manometer in the opposite deflection and see if we get the same conclusion. So now in a similar fashion, we apply the hydrostatic pressure equation between these key points again. So between point 1 and point A, that's this equation. Point A and point B, that's this equation. Point B and point 2, that's this equation. And then we use algebra to combine those equations to come up with an expression for P1 minus P2. In this case, we get P1 minus P2 is equal to the quantity rho O minus rho W times G times HAB. In this case, HAB is again positive because it's from the hydrostatic pressure equation, and that H is a distance, so it's positive. G is positive, again, but now we have rho O minus rho W. Rho O minus rho W is given as negative because rho O is given as less than rho W. So in other words, we've essentially verified our conclusion from the previous slide that the manometer will deflect towards the side of the lower pressure, as we see the manometer is deflecting towards P1, and P1 is shown to be less than P2. So just as in the previous slide, we showed that the manometer deflects towards the side of the lower pressure, here P2 is less than P1, and so the manometer deflects towards P2, and here P1 is less than P2, and the manometer deflects towards P1. So now essentially what this gives us is if we decide to analyze the tanks with tank 1 being larger than tank 2, or in other words, the level of tank 1 being higher than the level of tank 2, we know how to draw the manometer between them. Because if you don't and you kind of guess at the direction of the manometer, you can do that, but you might end up getting a weird negative sign somewhere and it's a little bit uncomfortable. So it's nice to kind of know what the manometer should look like for the arbitrary case that you decide to examine. So let's start to look at those tanks in the next slide. So now let's look at case 1, where case 1 we're just going to assume is tank number 2 drains faster than tank number 1. So tank number 1 will be at a higher level than tank number 2. And we can kind of see that here, tank 1 is at a higher level than tank 2. Since tank 1 is at a higher level than tank 2, if we go to the entrance of the manometer in both tanks, that means the pressure here in tank 1 is going to be greater than the pressure here in tank 2. So we know what that means for the manometer. The manometer is going to deflect towards the side of lower pressure, so it will look just like this. Now, let's decide to define A and B more specifically. If we define 0z, or z equals 0 right here at this ground level, then let's define B as z1 minus z2, and A as z0 minus z3. So the z1 and z2 is z1 and z2, the z0 and z3 is z0 and z3. Now, what we can do is write the hydrostatic pressure equation between all these key points again. So between point 0 and point 1, point 1 and point 2, and point 2 and point 3. So point 0 and point 1 are right here, point 1 and point 2 are right here, and point 2 and point 3 are right here. So now that we've written the hydrostatic pressure equation between all of our key points, all it's really left to do is combine those equations to determine how the heights between those key points are related to one another. However, the final result of combining all these equations and determining how these heights are related to one another is this result right here, which basically says that rho w times g times the quantity h01 minus h23 is equal to negative rho o times g times h12. Now h01 is defined as the height between points 0 and 1, h23 is defined as the distance between the points 2 and 3, and h12 is defined as the distance between the points 1 and 2. So h01 is this distance right here, h12 is this distance right here, and h23 is this distance right here. Now, it's important to note that those h's are defined as distances, so they have to be defined as positive numbers. And we will see why that's important on the next slide. So now that we have that final equation from the last slide, all we really have to do is map these heights to our key variables a and b. What we could see here is h12 is just the distance between points 1 and 2, so that's just equal to b. So we could take that h12 and replace it with b. Then we can multiply both sides by negative 1, and we get this equation right here. So now that we have rho o gb is equal to rho w times g times this quantity, we just need to map this quantity to a and b. h23 is the distance between points 2 and 3. It has to be positive. So the distance between points 2 and 3, you could just say z3 minus z2. So that's where this comes from right here, z3 minus z2. h0 and 1 is the distance between points 0 and 1, but that also has to be positive. So that is, as we see right here, z0 minus z1. So that's where we get the z3 minus z2 minus z0 minus z1. Now we're just simplifying this expression. Well, if we distribute this negative sign and then simplify, what we end up getting is rho w times g times this quantity right here. This z3 minus zo we get from that simplification is just negative a, as you see here. So that's where we get that negative a. z1 minus z2, well, that's just definitionally b. So that's where we get that b right there. So this is essentially one of our final equations. So now all you're really doing is taking the b terms and putting them on one side, factoring them out, and then solving for b over a. And when you solve for b over a, you see that it's equal to 1 over the quantity, 1 minus SGO, or 1 over the quantity, 1 minus the specific gravity of the oil. So for the specific gravity of oil, less than 1, so in other words, when the specific gravity of the oil is less than water, if b is less than 0, then a is less than 0, and if b is greater than 0, then a is greater than 0. So in other words, if SGO is less than 1, this right-hand side is always positive. If this right-hand side is always positive, then when b is positive, a is positive. When b is negative, a is negative. So if you go to the original diagram, we just kind of assume that tank 2 is draining faster. And what this is saying then is if this quantity is positive, this quantity is positive. Now, if this goes negative, or in other words, tank 2 becomes higher than tank 1, then this manometer will invert and will deflect in the opposite direction as we know it should. So what this essentially tells us is that this equation should be generalizable to the case where tank 1 drains faster or tank 2 drains faster. For good practice, let's check that second case and verify that we do indeed get that result. So now let's look at case 2 where tank 1 drains faster, and this is our new diagram, and we know that when tank 1 drains faster, the pressure here in the manometer is less than the pressure here in the manometer, and we know when that's the case, the manometer should deflect towards the side of lower pressure, so the manometer should look like this. We're defining A and B in the same exact way. We have our z coordinate defined in the same exact way, and we have 0, 1, 2, and 3 defined in the same exact way. We're writing the hydrostatic pressure equation for points 0 and 1, points 1 and 2, and points 2 and 3. And that's this set of equations right here. Now, what we're going to do at that point is the same exact kind of algebra we did for case number 1, which is shown on this slide right here. I won't go over that algebra explicitly. It's here for you to pause the video and look at if you'd like. But essentially, if you go through this algebra, then what you'll end up getting to is this expression right here. Now, this is kind of an analogous expression from case number 1, where we need to know what Z0 minus Z3 is, Z2 minus Z1 is, and Z2 minus Z1 is. So Z2 minus Z1, if we go to Z2 minus Z1, we could see that that is just negative B. That's negative B. So that Z2 minus Z1 becomes negative B, and that's what we see right here. Here again, we see Z2 minus Z1, that's negative B. Z0 minus Z3, well, if we go to Z0 minus Z3, that's defined as A. So we just plug in A here. And we're doing the same thing. We're doing our common factorization, solving for B over A. And when we solve for B over A for case number 2, we see that the final equation is again 1 over the quantity 1 minus SGO. So essentially, this is the equation that we need. And this equation applies no matter what the tanks are doing. Whether tank 1 is draining faster, or tank 2 is draining faster, or one starts higher and then it inverts, or the other one starts higher and then it inverts. Doesn't matter. This is the equation that applies. And now that we know that, we can plug in our knowns and determine what the amplification factor actually is. And we do that on this last slide here. Knowing that SGW is 1 and SGO is 0.797, plugging that into the equation that we got, we see that the amplification factor is 4.93. So for example, if tank number 2 is a 1-inch higher fill than tank number 1, then that might be kind of hard to see, or that might be kind of hard to measure. But that 1-inch difference in tank level corresponds to a 4.93-inch difference in manometer deflection. So when A is 1 inch, B is 4.93 inches. It's much easier to see a 4.93 inch difference than it is to see a 1 inch difference, especially when the tanks are this big. So with the order of, approximately a 5-inch difference in this manometer, that's going to be much easier to measure. That opens up the use of inductive switches, ultrasonic sensors, photoelectric sensors, maybe even cameras, or perhaps even visual inspection from an operator. So now, instead of having to measure what's happening in the tanks directly, you could just measure what's happening in this manometer and then map what's happening in this manometer to what's happening in the tanks. Okay, so that should be it for this video. I really appreciate you watching. Thank you very much, and I will see you next time.